are going to begin with our three competitors in the Master's Division. Our first competitor from the Department of Soil and Crop Sciences is Prajina Neupane. Prajina.
What comes to your mind when you think about global warming and greenhouse gas emission? Big factories and busy cities producing tons and tons of carbon dioxide, isn't it? But what if I tell you there is an even bigger villain in this story? Yes, nitrous oxide. Nitrous oxide is 300 times more powerful than carbon dioxide in causing global warming. And nearly 60 to 70% of human-caused nitrous oxide emission comes from agricultural soil, especially from fertilizer and manure application in the soil. So my research question is simple. How do we reduce nitrous oxide emission from agricultural soil? Now, fortunately, Mother Nature has solution to all of her problems. Like all our moms balance everything at home, Mother Nature tries to balance everything in the nature. So we have billions of microbes in the soil. Some group of microbes produce nitrous oxide, and other group of microbes, they consume nitrous oxide in the soil. And my research goal is to help these microbes consume more nitrous oxide in the soil to balance the production. We had three different treatments. One is chicken manure applied on the surface. Second is chicken manure applied with biochar on the surface, which is a charcoal-like material. And third is chicken manure mixed into the soil up to 8 to 10 inches deep. Both mixing of manure and application with biochar reduced nitrous oxide production by nearly 60 to 70%. So what changed? When we applied manure on the surface, nitrous oxide production happened at the top layer of the soil, so it could easily escape. Think of it as prisoners being held right next to an open exit door. Naturally, they all escape, right? So when we applied biochar with manure, it increased the number of microbes that can consume nitrous oxide in the soil. So think of it as prisoners being held right next to an open exit door, but this time we have more guards to keep them in. In our third treatment, when we mixed chicken manure in the soil, nitrous oxide production happened at the deeper layer of the soil, so they had to pass through soil pores to reach the surface and escape. Think of it as prisoners being held in a maze full of guards. Most of them never find the exit. So with this one simple step of manure mixing or applying it with biochar, we were able to reduce nitrous oxide emission by nearly 60 to 70%. So isn't that amazing? So again, reminding you one more time, we did not reduce the production of nitrous oxide itself, but we increased the consumption of nitrous oxide to balance the production and made it hard for nitrous oxide to escape. So lesson from Mother Nature. Balance is the key. Thank you.
We are welcoming from the Department of Mechanical Engineering, Valentina Torres. Valentina.
Global electricity demand continues to increase and is projected to rise by 4% in both 2026 and 2027. This growth is comparable to powering an additional 100 million homes a year. Every day, more people plug in, more cities demand cooling, and more technologies from industrial processes to data centers require more and more electricity. This trajectory cannot continue like this. The world must turn to processes that use electricity more efficiently. This requires materials with electrical conductivities optimized for a specific process and its operating temperature. But there's one challenge. Current materials that are economical at a global scale and easily conduct electricity do not perform well at elevated temperatures. Metals, for example, their electrical conductivities decrease and decrease a lot when they melt. In contrast, exotic dope semiconductors become more conductive with temperature, but rely on complex compositions that prevent their application at a global scale. My research focuses in developing composite materials suitable for extreme temperature environments with tailored optimized electrical conductivities. These materials are able to conduct electricity at elevated temperatures. You can see the microscopic view of the composite and how electricity flows throughout the material. I controlled this bulk property by compressing metal and ceramic powders into a low porosity granular mixture. by carefully selecting economic powders and abundant, controlling the emergent interfaces between them based on relative particle size, shape, and strength, and finally by fine-tuning their compositions, I can optimize their electrical conductivities for a specific application. The innovation here lies in controlling how particles connect together, the number of contacts created, their shape, and how tightly packed they are. These composites have already been demonstrated at the lab, showing tunable electrical properties at different elevated temperatures. Building on this, I used theoretical models to predict their behavior, helping me design and test new materials needed for real industrial applications. By implementing experiments with modeling, I'm designing scalable and affordable materials able to conduct electricity efficiently, even in extreme thermal environments, pushing today's conductors beyond their limits. We're at the edge of a new energy era, one where clean and affordable energy drives innovation and economic opportunity. And through my work, I hope to bring this future even closer. Thank you.
I want to introduce our final competitor in the Master's Division, Abigail Dwelle from the Department of Rangeland, Wildlife, and Fisheries Management. Abigail.
It's 6 a.m. in South Texas as my helicopter lifts off. Below, the mesquite glows in the morning light as we look for one small and underappreciated species, the javelina. Now, by a quick show of hands, how many thought this animal behind me was a pig? Well, y'all are not alone, but despite their similar appearance, this is not a pig at all. This is a javelina, and unlike pigs, javelina are native here in Texas, and they play an important role in maintaining healthy thorn scrub ecosystems and helping with seed dispersal. Wild pigs, on the other hand, are invasive and cause millions of dollars in ecological damage each year, and compete for resources such as food and water with native wildlife. So despite their similar appearance, it is vital that wildlife managers understand the difference between these two species. However, despite their ecological importance here in Texas, we know surprisingly little about them. The last time they were intensively studied here in Texas was in the 90s. And due to this, there's major gaps in knowledge of basic things like where they live and how they're interacting with other species like those invasive wild pigs. So, to fill those gaps in knowledge, we turned to helicopter surveys to map the landscape. Our surveys were conducted using low-flying helicopters that flew systematic transects across 10 ranches in South Texas. This encompassed over 200,000 acres. 2 observers looked at each side of the helicopter and recorded every javelina they saw and their GPS location. Since 2023, we've conducted 13 surveys and have over 206 javelina detections. We combined this data with long-term data from our partners at the East Foundation to get a data set of over 1,000 detections over the past decade. To map their use of the landscape, we first mapped each of the detections we saw. That's that first map you see up there. Then we overlaid those detections over a map showing the percentage of woody cover for the region. Then we created a resource utilization map, which is that very colorful one you see behind me, but basically just shows the density of javelina on the landscape. Red indicating more dense and green indicating less dense. Lastly, we created a linear regression that looked at if there's an association between that denser area of woody cover and the density of javelina. And there was. The more dense woody cover there was, the more javelina we saw. The next steps in this research are to repeat this, but see if there's an association with the presence of water, and also add pigs into the framework and see if they're changing their use of the landscape based off if there's pigs present. This information will be used by wildlife managers and wildlife biologists to better manage and protect the South Texas ecosystems and just give us some more information about this very unique Texas species. Thank you.
The next 7 competitors will all be in the Doctoral Division, and we are kicking off our Doctoral Division with Tessa Williams in the Department of Veterinary Pathobiology. Tessa.
Howdy, my name is Tessa Williams, and today I want to talk with you about something that you may already be familiar with, urinary tract infections. UTIs affect hundreds of millions of people each year, and more than half of all women will experience at least one UTI in their lifetime. What do you think of when you hear E. coli? You probably think of this bacteria as a common stomach bug that causes food poisoning. But what if I told you that E. coli can do far more than that? E. coli is the cause of 80% of all UTIs. This occurs when the E. coli from our gut finds its way into the urinary tract. From there, this bacteria can replicate and cause symptoms such as frequent and painful urination. Some people may think that although UTIs can be uncomfortable and annoying, they're relatively easy to treat, right? You can simply go to a clinic, pee in a cup, and receive an antibiotic prescription. Well, technically, yes, but there is already a well-documented rise in antibiotic resistance rates among these UTI-causing bacteria. This means that these organisms are evolving ways to outsmart and outmaneuver these medications. So what do we do when our current therapies are no longer effective? We identify novel targets, and we do it by using clues from our own body's immune response. If we zoom into the host-pathogen interface during a UTI, we can see that our own body's immune cells are utilizing trace amounts of copper to attack the invading bacteria. This phenomenon is known as nutritional immunity. As the name implies, we obtain essential nutrients like copper from our diet. But during infection, E. coli and other bacteria must hijack these nutrients from our bodies. Over time, we have co-evolved ways to withhold and obtain these nutrients from one another, like a tug of war. But just like in tug of war, what happens when one team lets go of the rope? The opposing team falls. When our bodies release excess amounts of copper during infection, it intoxicates and kills the bacteria. My project continues to investigate this mechanism. If we can identify precisely what makes E. coli susceptible to this copper killing, then we can leverage it as a strategy against UTIs. I see a future where we can harness our own body's nutritional immune response against these harmful bacteria. Thank you so much for listening, and please feel free to find me after if you have any questions.
It's time for our second doctoral candidate, who is, or a doctoral competitor, who is Leah Poellmann from Small Animal Clinical Sciences. Leah.
Imagine this. A perfectly healthy dog dives into a river. Playing, splashing, tail is wagging. A few months later, that same dog is dead. Not from an accident or old age, but from a parasite in the water. This parasite is Heterobilharzia americana, and it breaks all the rules. There's no prevention, no simple cure. Routine tests cannot detect it, and few veterinarians even know that it exists. Heterobilharzia enters through the skin when a dog swims. It then lives in the blood vessels of the gut, where it releases thousands of parasite eggs that cause inflammation in organs, leading to weight loss, vomiting, diarrhea, and even death. As veterinarians, the stories of certain patients stay with us forever. Drake was a Labrador retriever who loved the water. When he lost his battle against Heterobilharzia, we became determined to address this overlooked infection, because otherwise healthy adult dogs should not have to die from a parasite. This parasite was believed to be limited to the Gulf Coast states, and beyond that, very little was known about which dogs might be at risk and where in the country. When a handful of cases emerged in California, we began to suspect that this was not a local problem, this was spreading, and we wanted to measure just how big the problem truly was. We tested 727 dogs across the Southwest using 2 different types of fecal tests, and the results shocked us. Nearly 1 in 4 dogs, 24%, tested positive for Heterobilharzia. And for context, of all these dogs, only 6% carried the common types of parasites. In other words, not only does Heterobilharzia exist in this part of the country, it may be one of the most important parasitic infection affecting dogs in this region. We spoke to owners of positive dogs, and 97% of them told us that their dog had been swimming in the Colorado River prior to diagnosis. The river people in the Southwest turn to for recreation and escape. This essential body of water is likely the source of infection for so many dogs. All this parasite needs is water, a freshwater snail, and a dog shedding parasite eggs. Put these things together, and the infection can spread anywhere. Our research shows heterobilharzia is anything but a rare local phenomenon. This is a serious and widespread threat. Awareness is a powerful form of prevention, but now we want to go further, study ways to prevent illness altogether. We're the Drake Project, a research initiative created in the memory of Drake and with the purpose of protecting dogs who love the water as much as he did. Thank you.
Our next competitor is Tanay Kumar from the Department of Aerospace Engineering. Tanay.
Have you watched the movie Big Hero 6 or Iron Man and wondered if those tiny microbots or the Iron Man suit would come to life? I certainly did, and that blend of science fiction and imagination inspired my research. Now imagine a group of small robots, each an independent unit, but the real magic happens when they all come together, similar to a colony of ants, individually simple but collectively intelligent. But why do we even need such systems? Because the possibilities are limitless. Picture a disaster zone, collapsed buildings, dangerous terrain, and time running out. Instead of risking human lives, we could deploy hundreds of these robots. They could crawl into tight spaces, build bridges, or even lift debris to rescue people. Or think about space exploration. Humans are planning to colonize the moon and Mars. However, sending heavy machines is both costly and risky. What if instead we could send these modular robots that could organize themselves into complex structures, helping us construct laboratories, solar farms, habitats, all with minimal human assistance? But to make this vision a reality, these robots need to be more than just smart. They must be reliable, resilient, and efficient. Now, how do we make that happen? That's where my research on control theory, optimization, and machine learning kick in. Three powerful branches of engineering and mathematics that help me model and integrate this intelligent behavior. In my research, I have developed and simulated control algorithms that guarantee the stability of these robots even during the presence of disturbances and component failures. I also leverage optimization algorithms to determine the most efficient configuration of these robots that could achieve a given task with minimal energy while maintaining performance. Together, these methods form the basis of autonomous systems that can make real-time decisions, adapt to changes, and even perform when some of the units fail. The impact of this research extends beyond robotics, as similar principles can be applied to domains like medical technologies, where precision and coordination is crucial. In essence, I am bridging science fiction and engineering reality, helping us get one step closer to a future where autonomous robotic systems can help humanity grow and explore, both on Earth and beyond. So the next time you see microbots in a movie or Iron Man fly across the screen, remember, the future might be closer than you think. Thank you.
We are back with competitor number 7, coming to us from the Department of Mechanical Engineering, Pepito Thelly. Pepito.
So I'm actually going to start out with a little confession. Ever since I myself became an engineer, I get a tiny bit nervous every time I cross a bridge. And the reason for that is because I'm always like, oh gosh, I sure hope that the engineer who designed that bridge was paying attention in class the day that we covered structures. Like, let's think about that real quick. How crazy is that? Do we really go from a classroom writing down equations and drawing free body diagrams to all of a sudden now we're in the real world designing bridges that I'm going to be driving on? Like, what? Well, within academia, in order to bridge that gap between theory and practicality, we have labs and these things called makerspaces. Now, what is a makerspace? Well, picture a workshop, mills, lathes, 3D printers, and a whole other multitude of tools in a space where students can come in and build things. Now, the effectiveness of these spaces have been proven time and time again. They make better engineers. However, what is a bit more unknown are how these spaces behave. That's where my research comes in. What I do is I model these spaces like living ecosystems. And how I do that is I survey the space to see which user is using which tool. I then map this out in the form of a network. I analyze this network to identify certain underlying characteristics within the space. Now, one of the things that I've seen is that certain spaces allow for personal projects. What that means is if I want to build something, like let's say a model of a bridge, then I can just bring it in and build it, right? No questions asked. Whereas other spaces only allow for projects that are associated with the class. What my analysis showed is that in the spaces that allow for personal projects, students were using a wider array of tools earlier on in their academic journeys. And why does that matter? Well, early exposure has been shown to increase confidence, creativity, and build the type of engineer who says, yeah, I can figure that out. Because confidence doesn't just start from a textbook. It also starts from a space where it's okay to explore and get things wrong and try again. And for universities investing millions into these makerspaces, this helps answer a critical question. Which design choices actually unlock student potential? So moving forward, I'm going to be putting together these insights into a roadmap so that schools can build more effective makerspaces. Now, the next time you're driving across a bridge, I hope that you're not going to be thinking about me or this talk, because that would be kind of weird. But if you are, don't worry. Now you know that before that bridge ever even existed, there was a makerspace helping shape the engineer who designed it. Thank you.
Our next competitor in the Doctoral Division from the Department of Materials Science and Engineering is Sasha George. Sasha.
Not an earthquake and not a wildfire. In 2015, over 8,000 families in California lost their homes to something far smaller, bacteria. They found deep underground, bacteria was attacking metal storage tanks until one cracked, resulting in the largest methane gas leak reported in the US. It sounds unbelievable, right? Bacteria causing an industrial disaster, but we already know that they can be powerful. They attack our immune system and make us sick. But here's the truth. Less than 1% of bacteria actually cause diseases. The rest, they're harmless or even helpful. For example, probiotics, good bacteria we find in yogurt. They protect our gut and keep us healthy. Now imagine we apply the same idea to not our bodies, but something much bigger, our cities. Buildings, bridges, pipelines, even cars, anything made up of metal that are surrounded by bacteria all around us. The bad bacteria can attack the metal by corroding them, causing holes and cracks to form. Over time, this can result in failure in the metals, things like pipelines leaking to catastrophic accidents like bridges collapsing due to weakened bridge joints. In this case, the bacteria, they kind of sound like the villains, right? That's where my research comes in. I focus on engineering the bacteria to transform them from villains to superheroes. So how do I do this? Well, I work with a team of genetic engineers that help us modify strains of bacteria. I then run in-lab experiments and computational models to help us identify the best strains that can protect and defend the metal in 3 different stages. In the first stage, they can cover up the cracks and passivate them. In the second stage, they form a thick protective biofilm coating over the metal. This acts like a physical barrier, preventing outside bacteria from attaching. In the third and final stage, they can grow fast, outcompeting the bad bacteria, pushing them away. So it's simple. Just like how good bacteria can protect our bodies, they have the potential to protect our cities by keeping our bridges, buildings, and pipelines safe. So in my research, I focus on engineering stronger metal structures by transforming bacteria from villains that destruct to superheroes that can protect. Thank you.
First, from the Department of Biomedical Engineering, Thalma Orado. Thalma.
Meet Janet, a patient living with diabetes. This underlying condition can make it difficult for the body to heal itself. when injury happens, leading to chronic wounds. Every day, Janet worries if her wound is quietly getting infected. You see, infections in chronic wounds are often caught too late, leading to frequent and long hospital stays, the use of heavy antibiotics, and sadly, even amputations. Within the next 1 hour, 10 Americans will lose a limb due to diabetes-related amputations. Current available methods to detect infections in chronic wounds involve taking a part of the wound and growing it in a petri dish for up to 72 hours to obtain a report, making this process too slow, unreliable, and needing specialized personnel and facilities. And for people like Janet, every moment lost matters. That's where my research comes in. I designed smart polymers. These aren't your everyday plastics. They're special, high-tech biomaterials which can remember their shape and with the right chemistry can sense when infection is happening. How do I make these? Well, in the lab, it's a little bit like baking, except instead of sugar and flour, I use small blocks of molecules called monomers, adding them together in a process called addition polymerization to form larger blocks called polymers. And just like a chef tastes their food, I characterize this to determine, are they safe? Are they strong enough? Do they behave the way I designed them to? And once they pass this test, it's time for the real challenge, putting them up against nasty bacteria behind chronic wound infections. So far in the lab, I have achieved a material which has a green glow, just like the traffic signal, meaning Janet can go on about her daily business because her wound is not infected. But when infection begins, this material loses the glow, alerting Janet and clinicians to stop and start antibiotics to address the infection. I'm currently working to make this material's color change easily detectable by the eye. Imagine Janet wearing a bandage which warns her with a simple color change the moment infection starts causing trouble. No guesswork, no delay, just faster treatment. If wounds can talk, they can tell us when infection begins. We can step in sooner and heal faster and better and prevent millions of people like Janet needless suffering. I'm giving wounds this ability.
We are at our final competitor for the evening. Our last competitor for the evening from the Department of Oral and Craniofacial Biomedical Sciences program in the College of Dentistry is Paria Dehghanian. Paria.
Have you ever thought about how you talk, eat, or smile? Probably not, until it hurts. Everyone, try this with me. Put your finger right in front of your ear. Now move your jaw side to side. Did you feel it? This is your jaw joint. Your jaw joint is the coolest joint in your body. It moves up and down, left and right, and even rotates. Without this joint, you couldn't eat anything. Without this joint, you couldn't say any words. Without this joint, life would be so difficult. But here is the problem. 1 in every 3 people will experience pain or dysfunction in their jaw joint at some point in their life. Some of you may have felt that little click when you chew or yawn. It could be a simple clicking or popping, or daily pain, trauma, or even jaw lock. Unfortunately, jaw joint disorders are one of the most challenging conditions to treat. And here is where my research is trying to help. Imagine a chicken drumstick. This is the bone, this is the muscle, and the muscle attaches to the bone through tendons. I study these tendons in the jaw joint of mice. And exactly where the tendons attach to the joint, I discovered an entirely new type of bone that no one had described it before. When I compared this new bone with the conventional bone, it was completely different in terms of the shape of the cells, the calcium level, and the way it grows. Even more interesting is that this new bone kept growing as the mice started chewing and using their jaw joint. Next, I genetically traced the tendon cells over time, and the results were surprising. The tendon cells didn't just stay in tendon. Instead, they gradually became bone cells, and the cell change increased day by day. This is crazy. It's like watching an apple gradually turn into an orange. So, in summary, I discovered a completely new type of bone, the tendon-formed bone. And it matters. Why? Because before treating any disease, we first need to know how things work in normal situation. This new discovery might be the missing key explaining why jaw joint treatments are always challenging. By harnessing this natural ability of tendon cells in forming bone, we can hope for better and more advanced regenerative therapies of jaw joint in the near future and helping many people. So, next time you bite into an apple, remember, your tendons aren't simple connectors. They are builders and maybe future healers. And I'm working to make that future real for your smiles, for your wellness. Thank you.